So first of all, thank you to all the speakers, to Eric and to Caslav and Nuryia. Now we've seen three aspects of Wigner's friend thought experiments. And now the question is a bit what to make of it now. And yes, so the first thing we could do is we could go back to questions that were arising after Eric's talk. So maybe we can ask Bernardo to show some of the questions that have shown up. And then we can see whether we can discuss those as well. Or put them into context of the other talks that we've heard. Okay, so this is something that was asked to Eric, but probably you can ask this also to Caslav. The question was, does absoluteness of observations imply that the observed event persists in time? That is, that if the same observation is repeated, that the outcome must be the same. And I think that this is a good question because it hints at some other aspects of what's happening in these experiments. For example, that you have a memory erasure involved typically in these situations. And the question is, what's the significance of that? Maybe Caslav, you have something to say about that. We've given it some thought.
I would have something to say about that, and thanks for the question. And actually, there is a paper dedicated to this question in our group, in which we consider really one friend making certain observation in the past, and then there is unitary intervention of the Wigner, and then there is again observation of the friend, and the question is whether the particular question that we were concerned with, and it's related to your question, is whether we can consider the past events, facts, as objective as the one from the present, meaning these two time instances, and which we usually have in classical physics. Now, there is this intervention of the Wigner in between, which one can say, well, in that moment, you really erase the memory of the friend, and then you have another observation, and then since you erase the memory, there is no meaning of talking about things coexisting or in the same sense objective in the past as in the present. But however, and this is, I think, the message from the quantum, and it's very important, is that we can, even in classical physics, erase the memory and replace with some other enter. However, there is no problem whatsoever to assume that there was a record in the past, although we don't know anymore because it was erased in the meantime. Now, in quantum mechanics, you go beyond that and say, even if I imagine there was a well-defined outcome before intervention of Wigner, although I don't know, even just imagining, and this means like I imagine that there was some joint probability for coexistence of the events in the past and the present, will run into the contradiction with the probabilities as predicted by quantum mechanics. And so it's not only that it's erased, it's really there is no sense whatsoever to talk about existence of these events in the past, if quantum mechanics is correct.
Yes. There was also discussion going on at some point about the significance of this erasure of information in relation to the Flauchiger-Renner experiment that Nuryia was talking about. I think Scott Aronson on his blog wrote something about, look guys, it's certainly very hard to think if your brain gets Hadamard. Yeah. But then Renato's answer was, well, yes, the brain gets erased, but it only happens after that agent does its reasoning. So then maybe we can pass this on to Nuryia as a question, like how, for example, when you model it on a computer, how this temporal succession of events plays a role here. So I think it is relevant for the thought experiment and for the conclusion that somehow the observer first does its observation and then predicts, and only later on gets measured and hadamarded by the outside observer. Is that true?
So indeed, this is what happens. So in this case, actually, like so one thing is that not only the agents get hadamarded, but the whole lab gets hadamarded. So in a sense, what the outside observer does, they also reverse the reasoning process, and then they hadamard it or measure it in above basis, like the original two, the measured system and the memory degree, which corresponds to storing that measurement outcome. And what happens to the inferences, they get combined in successive order. So they don't all get combined with like at the end, but either basically Bob's prediction. So Ursula's prediction is combined with Bob's prediction, and Bob's prediction is combined with Alice's prediction in such a way that in the end, the final prediction about Wigner's outcome is made by Ursula. Mm-hmm. Okay. If that makes sense.
Yes. All right. Okay, but I think in any case, both these answers kind of hint at the memory erasure not playing a foundational role, even though it plays some kind of practical role in this thought experiment. You kind of needed to set it up, but it's not clear why this erasure process undermines the usual reasoning that you would want to put out here, or why it directly tells you that there hasn't been an outcome. So. Maybe that relates to another question here that was addressed at Caslav from the audience. What is your definition of observation of fact? Does it coincide with the act of recording? I mean, you already said a little bit about that, but maybe you want to say a bit more, given that it was asked a couple of times here.
Yeah, I'm not sure I can give a definition, but I don't think of anything different than what's happening all the time with us, and so I would say some immediate perception, like click, like that's a fact if you hear that what I did on. So immediate experience in terms of the clicks or lightning or the things that we cannot take from with our senses. However, if I would need to make a physical definition, I feel that in terms also to quantum mechanics, saying that there is no phenomenon like this observed phenomena, that I need a certain sense of irreversibility. And what I mean with this is that usually when we want to describe something before measurement, we take all these degrees of freedom and we evolve this unitary. And now at the moment when particle or a system interacts with our measurement apparatus, we lose this ability. We say, oh, there are many degrees of freedom in this measurement apparatus, so I cannot follow them all. And so what we technically say trace over, meaning ignoring the most all the details of measurement apparatus. We don't think about whether atom is like that or in that configuration measurement apparatus. We just only want to know, does it click or not? And that's very coarse-grained. And so in that sense, it has something to do with irreversibility, the appearance of the fact. And now, of course, Wigner's friend situation is exactly paradoxical because it should be irreversible in order to have effect. And nevertheless, Wigner can unitarily handle this everything. And that's why I concluded that even the notion of irreversibility should be observer dependent. It's for all practical purposes irreversible for us with our means, with our ability to reverse. But maybe it's some more an experimentalist with a higher budget for experiments can actually treat this unitarily, but he himself will have his measurement apparatus to make sense out of his quantum description.
So in a way, this hints at some thermodynamic relation as well. So I think there's even a paper by Matteo Lostagliu where he argues that there's a conceptual similarity to Maxwell's demon, where you also have two different perspectives, either that of a physicist that just looks at the system, or the other perspective is that by the demon who can see the microscopic movements of the particles. And in a way, we have a paradox, but not really, because the state assignment is already, even in thermodynamics, makes sense to do that, to see that as observer dependent. So I wonder if there would be an opportunity to explore more of this relation, or what to make of it. But let me see what other questions we got here. So one question goes to all of you. So it says that Hossenfelder dismisses Proietti et al. By stating that photons are not observers. How do you react to that? So, Caslav, do you remember which experimental paper that was?
That was an experiment that was testing my Nobel theorem.
Oh, yeah. Right. Okay.
In Petrizi's group, if I am not mistaken, yes.
Yes,
because it
correct,
was also mentioned by Eric, this experiment.
Bernard just said this is, yes, that's it.
Yeah. I mean, I think that this experiment is not an experiment, not answering the question, and for good reasons, is not ultimate experiment, or not even a significant step towards the Wigner's friend, because indeed, I would also say the photons are not observers. However, there is some value in making these experiments, because what we are coming up with all these different no-go theorems is actually trying to pinpoint on a set of different sets of assumptions that leads to inconsistencies when compared with the quantum predictions, and they have a different flavor than the original Bell's theorem. So I think it's good that we do that, and it's good to go in small steps, but I also feel that we should, that it's very hard, but maybe the real question is, what is an observer? And then, of course, given this definition, and I think Eric tried to do his, what he thinks is the right direction, to make steps towards that kind of experiments.
Yes. So it seems to me as well that this is a very worthwhile pursuit. Still, you might in general ask, and I would like to, again, quote here Scott Aronson, who sometimes says, yeah, we've done all this and that foundational experiments, and it gives us exactly as whatever is predicted by the Schrödinger equation. We do another experiment, it just gives us what is predicted by the Schrödinger equation. So in some sense, the experiments that we're doing in quantum foundations are very different from the ones that are done at the LHC or so. So because in some sense, nobody really expects a deviation, at least for small systems. So we're kind of very slowly going upwards. We do experiments that we believe we have a very strong control and we know what to expect, and then we try to perhaps make them more complex, and at some point arrive at experiments that come close to the paradoxical thought experiments. Right. But it seems, yeah, there's a bit the question about what we want to achieve with these in principle experiments with small systems when we do them. Okay. What other questions do we have? We have a question for cubists, but maybe that would be something to ask for tomorrow. Okay, so there's another question that was directed at Eric first, but maybe we can puzzle it out together or see what the relevance of this is. So it's about the assumptions physicalism and ego absolutism, and whether these are already in contradiction. Because physicalism says that thoughts have no reality beyond the physical phenomena that sustain them. For example, neuronal electrical activity. Hence, they cannot be real in the sense of ego absolutism. So perhaps maybe then that this is embedded into a more general set of questions, which is what is really the relevance of talking about observers here and about people that have experiences that we put into these thought experiments, and what's actually in the end the difference to the microscopic experiments that you do with photons, for example. You could say technically, for example, something that you pointed out, Caslav, technically, if you just have two spins, it's hard to say that one spin is an observer because that spin cannot have orthogonal records about the other system. But I wonder if this is really what we want to do, about this big elephant in the room, that actually what we want to ask is what would it feel like to be in that situation? Do you agree?
No, I agree. That's why I thought that at that level it was really showing that we should be careful by extending experiments on let's say on quantum systems to this domain, and that there is a difference. But I don't think that we capture the full relevance of the fact that we mixed observers with quantum systems or put in the different roles. And sometimes I also think that maybe quantum theory is not done for the biggest friend type of experiment. Maybe it's beyond the domain of quantum theory, so that the experiment will not be sufficient, not because there is any physical scale in which this will not work with the superposition. It's just that this is not what quantum mechanics was proposed for. But I'm super careful about that, and it seems to me that maybe there is a deeper reason why there is no sense in this experiment, although I'm enjoying doing the same. Yeah.
Yes.
Yeah.
Nuryia?
I think I agree with this point, because somehow the way I kind of learned to see this extended bigness scenarios over the years is basically what they tell us is something about the knowledge of these agents or their outcomes, or whatever language they use to talk about these outcomes. And to me, the results, the contradictions that we get in these no-go theorems might point to maybe the language that they use is simply not enough, as Caslav said. Maybe this quantum theory, quantum theoretical description is not enough. It needs to be somehow adjusted or complemented by something. So yeah, my general idea of this no-go results is maybe we need to think more carefully about the language that we use when we describe them.
Yes, the language we use to describe them, and the unspoken assumptions that we put out when we want to reason and argue about the efficacy of doing so, right? So this is something I would, since Jacques is also here, another homework for the cubists, right? You could say, well, whenever we have a state assignment and a probability assignment, according to your point of view, this is all about betting odds and then waiting, and in the end of the experiments you actually either get money or you don't, and you better remember which bet you've placed and so on, right? So perhaps there's something that's not even specifically quantum, but that has to do with probabilistic reasoning in general that may go wrong as soon as observers are put into very extreme situations in which they lose their memories, for example. Yeah. Certainly it cannot be that easy, because earlier on we've discussed that just erasing one's memory is no way out of some of the paradoxes. But I think there might be something to be learned about the relevance or the operationalization of what we even mean by probability, for example, as betting odds. And whether we are here just in a regime where we cannot, that doesn't apply to the usual betting scenarios, and so we shouldn't expect our theories to give us successful answers for tasks that they were not built to do so, right? Maybe, yeah. Okay, so we have two more questions that are somehow a little bit not directly to the point of the talks today, but let me nonetheless read one of them. So it's a bit unfair because we don't have anybody here that defends relational quantum mechanics directly. But nonetheless, so the question is, what are your views regarding Rovelli's relational quantum mechanics and the notion that it is relations all the way down? Doesn't it lead to infinite regress? Yeah, I know that Caslav has thought a lot about this. I'm putting it up also.
Yeah. I think there is something valuable in the idea of relationalism, and also I conclude in my talk with the possibility of relational fact. But a relational quantum mechanics is more than that, and I think it was also born from the idea that we should be able to talk about quantum theory outside of the laboratory framework, outside of this operational framework, because I think that the proponents of this idea would say, like, well, there was a quantum system even before the first agent came into his existence. And then what in this aim, which is justified maybe aim, I think that there is some methodological step that is very critical and which I would disagree with, and that's that. Then they say, okay, we know how it's the situation in the laboratory just for our experience, so we can speak about spin processing in the magnetic field. We can talk about directions of the spin, then positions, and so that experience from the laboratory, together with the idea that there is no difference whether it is a laboratory situation or otherwise is a situation where there is no laboratory, but there are just physical processes around that, I think motivate them to take the same language and same categories from the laboratory into systems where there are no laboratory, there are no agents, there are no measurement apparatus. And then they start to talk about, oh, that's one spin, small rotating around another spin. Although there is no resources, there is no even facts happening there. There is no clicks. There is nothing clearly what's happening there. And so so this idea was also to avoid the measurement problem and so on, because there is no difference whether there is a measurement apparatus or not. But to me, it seems just the opposite, that they installed the measurement problem where it was not before, namely at the level of two spins. Because I can ask myself, well, when does one spin experience the other one being up? Does it happen now, continuously, later on? What happens in between? How often one spin observes the probabilities of the other spin? So all these questions that we ask in the laboratory case and that are related to measurement problem, I actually install now where there was no problem, because we didn't think about that as any happenings on the level of the two spins. And I think this part is problematic, and also, yeah, I have this. I think that it should be distinguished, that the part that talks about relationalism in the sense of the facts and observations, and the one that wants to go beyond that.
Okay. Yes. So I think. Anyway, it would probably be fairer to have somebody directly be able to answer, right? And there's been another paper by Carlo out as well. So maybe I don't want to get too much into detail for this now, but I guess it was interesting for our audience to just get a reaction to this. Now, okay, so let me see what else we have here from the audience. Okay, one of them, good. So one question is again going to all, which is also not quite to the point, but still interesting perhaps. It asks, can we say that all loopholes of Bell-type experiments have now finally been addressed after 40 plus years? And now perhaps in this context of no-go theorems that we've seen today, we can perhaps extend the question by asking, would there be any significant loopholes that prevent some of the conclusions that we've seen today. So yeah, it's a bit something that I haven't really given it too much of a thought, I must say. Certainly we had experiments in 2015 that closed all significant loopholes, I would say, for bell-type experiments. And I guess my personal view would be that what else should we do? So at least for microscopic systems, local realism has been disproved, except there are always the possibility that something surprising happens for larger systems, as some collapse models would say. But I don't see why we should expect that to be the case. But I don't know what the two of you would say there. Yeah.
I agree with you. I don't know, maybe the question was also addressed to something which is sometimes called freedom of choice assumption. But I wouldn't say that's a loophole that it can be closed, because I don't see a way how one can disprove the possibility that everything is super deterministically predetermined. But I also don't believe that's a plausible assumption, and this possibility raises more questions than answer, because as we know, if you have reduced the freedom of choice, you can violate Bell inequality stronger than quantum mechanics. So the question is, why don't we see this? So then any input or idea that would explain why we see 2 square root of 2 instead of 4, what is the maximum relation, is to me much more profound than the idea that there is no freedom of choice.
Yes, I also agree, and I think there's a difference, for example, to other claims when you say maybe you have an objective collapse model, so you'd say there's something about quantum theory that we haven't seen yet, but here's a concrete model and a concrete prediction where we can look for it, then this is of some value. But just to say that in principle there could be superdeterminism and we're not really free to choose our settings, even though it looks as if we were free, and without saying how this could be verified in some sense and how it comes about that then we only see non-signaling correlations up to the specific value of the CHSH violation, not other things, that I find just not fruitful. Right? So this is why I think these kind of discussions about loopholes are in some sense not fruitful, except they have been fruitful in extending our technological abilities to close these potential loopholes. Yes. Is this the final question that we have from the audience? Okay, so yes, so one question again from Jacques is, do observers need to have a language, a system of meaningful symbols in order to qualify as observers? Now looking at my 4-month-old baby, I have to say, Jacques, no, but maybe, I don't know. So let me ask Nuryia, for example, in the Frauhiger-Renner experiments and in the way you model it, the reasoning chain, is this always thought of actually being done by the observers that are involved in the experiment? So should I really think of them as being able to talk and reason? Is this somehow crucial?
I think what is crucial is that they're somehow able to express the fact that they get some sort of outcome. So they there should be some measurement interaction. And another thing, even more crucial, is that somehow they're able to communicate to each other. Maybe it's on the language. Maybe it's, I don't know. Even the fact that they have to have a shared understanding of what is spin up and spin down. So what to have like this common maybe huge reference frame or something of that manner. But I think like when I was saying having this language of agents, it's more alluding to the fact that they're somehow able to compare their results and talk to each other about their results in any manner. And I think this is a very reasonable assumption to make, unless, I don't know, you're a cubist and you only care about your own predictions about the world around you. But if you want to communicate with somebody else and not have this, kind of, in a sense, solipsistic view, then you need to have some common points. And this is all the language is about.
So still it seems a bit like, say, in the Frau Higarena experiment, that it's something weaker than actually open communication. Somehow, sometimes you close agents off from the others. And I agree, Nuryia, that certainly we need some amount of that. Perhaps in the beginning of the experiment, they should all agree on the protocol. And maybe they want to tell each other what they will do later on. But it seems there's some stages where you explicitly forbid communication. Like.
Yes, indeed. Yes. But yeah, I agree that indeed this. But some conventions, they have to be fixed before that.
Yes. Okay, yes. Yeah, I think exactly. So, but that seems to be somehow the basis of even setting up an experiment. You need that all the PhD students and physicists involved need to know what they do, and they need to be educated enough to handle the stuff that is involved in the experiment. So this is something, perhaps a more practical question than the earlier question that we discussed about how we should actually ontologically define an observer or something like this. So maybe these are separate questions. Okay, but time is slowly running out. So this was, I think, a very, very interesting day. Let me thank everybody again. So thanks to Eric, who is asleep now. Thank you, Caslav and Nuryia, for the very nice talks and for the great discussion. And also thank you, everybody, for joining us online. Tomorrow we'll have another day of talks. You'll find the program also on the Essentia website. And with that, I would just like to, say thanks again and have a good evening wherever you are in the world, and see you again tomorrow. Yeah. Bye-bye.